we're going to take a look at what's probably our most valuable tool in the world of logic, and that is the conditional statement. Conditional statements are going to allow me to really put together a lot of ideas and build some thoughts of. So let's just go ahead and define it. So a conditional statement is a logical statement made up of a hypothesis and conclusion. So this is going to be the case for many of the things in this video, is that it's going to be one that's going to be best demonstrated with an example. So I'm going to give you a conditional statement. A conditional statement here would be something like, I'm going to use this one a lot. If it is raining, comma, then there are clouds. So this is a statement here. It contains two parts. It contains my hypothesis, which is this part. This is my hypothesis. And it also contains my conclusion. Then there are clouds. Conclusion. And so they're pieced together with these two words, my if and my then. So what I'm trying to say is that if this is true, in this case my hypothesis, it is raining, then something that is necessarily going to be true because of it, something that follows because of it, is the conclusion. There are clouds. So this is an example of a conditional statement. They're always going to follow this format. If something is true, that something is a hypothesis, then what will follow is there are clouds, the conclusion of my statement. So these statements are sometimes going to be true, sometimes going to be false, but really our goal moving forward is to build true statements. Something that will always be the case, that if my hypothesis is true, then my conclusion also is true. So let's look at a couple more things that go along with this. So the negation of a statement then is just a statement that has the opposite value of the original statement, or opposite meaning of the original statement. So if I have something like a statement like the ball is red, then my negation is going to be a statement. It's pretty simple. The ball is not red. So this is something that obviously has the opposite meaning, and it's the complete opposite of what I had initially. We can see or think of something that's a little bit more mathematical. Like if I have a statement that x has to be greater than 4, so it's not always going to have the word not in it. I want to think of what is the statement that has the opposite meaning of this, and so the opposite meaning would be, well, if x is greater than 4, the opposite meaning would be x is less than or equal to 4. So most of the time, my negation, I will use not, or take out the word not, but sometimes I'm just going to talk about what the opposite meaning is in general. I guess another example I should show you is if I say, well, let's go with it is not raining. The negation of that would be it is raining. So it doesn't actually have to contain the word not either. It could be taking out the word not. It just has to have the opposite meaning of what I had previously. So we've talked about conditional statements, talked about negations. Now we should take a look at, well, what happens when we put those all together. We can talk about a set of statements. So there are three new things here that we want to address, and I'm not actually going to give definitions for any of them. They're really hard to give definitions to. What's going to be best is just looking at examples. So these are the converse, inverse, and contrapositive. So if I have an original conditional statement, in this case it's going to be if it is raining, then there are clouds. I can have three different statements I'm going to construct based off of that relationship. The converse flips the hypothesis and the conclusion. So the converse in this case would be if there are clouds, then it is raining. I'm also going to use a shorthand for this. So I'm going to use a couple variables. These variables in this case are not going to be for numbers. They're going to be for statements. This is going to be the statement if P, then Q. So in this case, it is raining is P, then there are clouds is Q, the then is the arrow. So if P, then Q. The converse of this then, if there are clouds, then it is raining, would be the same thing as if Q, then P. All right, so I've just flipped my hypothesis and my conclusion. The inverse is my original conditional statement, but I'm taking the negation of each of these. If it is not raining, then there are not clouds. The way that I shorthand write this is that I use my negation symbol, which looks like this. So if it is not raining, so if not P, then not Q. And then last but not least, my contrapositive, which kind of does both things. It flips my hypothesis conclusion and takes a negation of each. So this would be shorthand, if not Q, then not P. So these four statements are all related to each other. They have the same core parts, these P's and these Q's, but the order in which I have them, whether or not they're gated, matters. So we can also talk about like the relative truth of these things. Now, if we're taking this, seriously and not looking for, weird examples, it is generally true that if it is raining, then there are clouds in the sky. That is a true statement. If it's raining outside, the rain's got to be coming from somewhere. It's got to be coming from the clouds. So the converse, on the other hand, if there are clouds, then it is raining. This is a false statement. It will not always be the case that if there are clouds in the sky, then it will have to be raining. Okay? If there are clouds in the sky, then it might be raining, but this does not necessarily have to follow here. We don't know if that's the case. My inverse then says if it is not raining, then there are not clouds in the sky. So this is also false, because if it's not raining outside, then there are not clouds. Well, there could still be clouds in the sky, even though it's not raining. And last but not least, my contrapositive, if there are no clouds, then it is not raining. And this is true. If there are no clouds in the sky, then there can't possibly be rain because there are no clouds for that rain to come from. So this will not always be the case that, my conditional statement, if it's true, that my converse and inverse are false and my contrapositive is true. It could be the fact that they're all true, or they could all be false, or my conditional, my contrapositive be false, my converse and inverse are true. But there are certain pairs that really matter. So my conditional statement will always have the same truth value. I'll label these then. The conditional statement will always have the same truth value as my contrapositive. And my converse will always have the same truth value as my inverse. And so we actually have a name for these. We have a name. So let me get rid of this for a second. We have a name for what that is. And the name is equivalent statements. So an equivalent statement, or equivalent statements, are statements that have the same truth value. Okay, have the same truth value. So in this case, if I go back to my previous example, if it is raining, then there are clouds, and the contrapositive of that, if there are no clouds and it's not raining, would be equivalent statements. They have the same truth value. They're both true at the same time. If I have two statements that are both false at the same time, they would also have the same truth value and thus be equivalent statements. Then, last but not least, our last thing we have to define is the biconditional statement. This might be the most important of them all, besides obviously the conditional statement. And it's a statement that contains the phrase if and only if. So if and only if, what does it mean? So if and only if means, if I were to expand on this, is that if something is true and only if that something is true, then something else is true. That follows. Which is a confusing way of saying that it goes both directions. That's where that bi comes from. Biconditional means that it goes both directions. So biconditional statements make really good definitions. So let's look at a definition here. This would fit. I'm going to give a definition for what a right angle is. So a right angle, as we know, is an angle whose measure is 90 degrees. And so I'm going to write this definition in biconditional statement. And so I can write it like this. So an angle is right if and only if its measure is 90 degrees. Okay, so here's what I'm saying is that an angle is right if and only if. The only way it can be true, and the only way that this is true as well, is if they're both true together. If and only if its measure is 90 degrees. The reason I can say this is biconditional is because I can read this in both directions. If I were to write this as a conditional, if an angle is right, then its measure is 90 degrees. And I can write the reverse of this. If an angle's measure is 90 degrees, then it is right. Okay, so I can go in both directions here. Either of these statements is fine. All right, so it's more than just a conditional statement. It's saying that if one is true, the other is true. It goes in both directions, if and only if each other are true. Okay, so biconditional statements, like I said, make really good definitions. They go in both directions. The shorthand for this, by the way, is an arrow that goes in both directions. So we'll expand on these more later. But these are kind of like our building blocks for logic that are going to allow us to say really meaningful things later, and actually are going to be very helpful for us when we actually start writing proofs.